Hey everybody, welcome to this tutorial on how to build with Superfluid. I'm Sam, I work on DevX here, and today we're going to be walking through the tradable cash flow contract. So the tradable cash flow has become a bit of a staple within our examples repository because it's used quite often as a primitive within hackathon projects and production apps. So the cool part about the tradable cash flow, and the reason we're going to walk through it step by step today, is that it is a Superfluid super app. So what is a super app? Well, a super app allows you to automatically execute specific arbitrary logic whenever a specific Superfluid related operation takes place with regard to that contract. So in the case of the tradable cash flow, what it can do is receive streams, and upon the creation, update, or deletion of that stream, it can then do something. In our case, what it's going to do is send 100% of the incoming cash flow to whoever the owner of the contract is. The tradable cash flow is also going to be an NFT, so it's going to allow us to tokenize a money stream and ensure that those streams follow the holder of the NFT even after it gets traded. So if we look at this example here, let me share my screen here. We can present. This is what our tradable cash flow is going to look like. We have incoming streams there on the left, and then we have super app custom logic there in the middle. You can think of that green outlined box as being our contract that is also going to have the super app functionality. And then what it's going to do is make sure that all of the outgoing streams are sent to the owner of that NFT. Again, to recap, streams go in, they're going to be automatically routed to the contract's owner. And because it's an NFT, the streams are just going to follow the NFT to the new receiver. Okay? So you can find this example inside of our main examples repository. I'll show you where you can find this here. So let me expand this just a bit. What you can do is go back into our monorepo, go to examples, and then you'll see here the tradable cash flow is sitting right here, right? So we have the contracts we're going to use. We have some helpful scripts you can use. And we have an example test suite that also might be helpful for writing your own tests, right? So I recommend reviewing this as well. In our case, though, let's just go through step by step and walk through the contract. Okay. So I have the RedirectAll contract up here. The RedirectAll contract you can think of as the main logic contract, which our NFT will inherit from. You can see here inside of the tradable cash flow itself, it's an ERC20, so it's an NFT, and it also inherits from the RedirectAll. And you can see we do some things here in the constructor. We mint the NFT, and then we have a function here we'll walk through later. But we need to walk through the RedirectAll contract to really understand what's going on. So at the top of the contract, we have our Superfluid imports. Right, we're going to import some key contracts that are critical for interacting with the Superfluid protocol, including this iSuperfluid contract, which is the Superfluid host. And for those of you that are new to Superfluid, you can think of the host contract like the brain of the protocol. We also import the super app base contract, which allows us to include some of the functionality around the automatic Superfluid callbacks that are triggered that we'll walk through in just a bit. And then we include the constant flow agreement contract, which allows us to interact with the money streaming functionalities, and we'll mainly use this for reading data on specific money streams. And then finally, we will import the CFA v1 library, which will allow us to create, update, and delete streams in a very easy way with basically just 1 to 3 lines of code. Okay? So we have a couple of state variables we need to keep in mind. One is this CFA v1 library variable, which will initialize using this syntax for including the library. So using CFA v1 library for CFA v1 library.init data. This just allows us to initialize it here, which we'll do in the constructor in just a second. We then take this and actually do assign it to a variable here called CFA v1 lib. We have a constant, which is just the hash of this string to give us the bytes hash of this Superfluid address. And we have 2 more. One is the receiver address and the accepted token for our contract. So in our contract, what we're going to do is essentially whitelist a specific super token that you can use you could expand this out so that this is compatible with any super token, but you'd have to change a couple of things to do that. So we'll just leave this as a contract which can execute this functionality for a single type of super token. All right, so then inside of the constructor, what we do is we pass in the address of the Superfluid host contract, right? That's necessary for the initialization of our library so that we're actually interacting with the correct deployment of the Superfluid protocol. We then pass in our whitelisted token and the initial receiver, right? So who is the initial receiver on all the streams coming into the contract? Who should this initial, effectively, owner be? We will pass this down inside of the tradable cash flow contract when we first mint the NFT, but just keep in mind that we are going to specify who that first receiver is. We run a couple of assertions then to make sure that none of those addresses are the zero address. We assign these variables here in the accepted token and receiver, and then we initialize the CFA v1 library. So you can read more about this in our docs, but what we're doing here is just passing in the host address and the address of the constant flow agreement contract using this CFA ID, which is this hash here, to help us just do this in a way that prevents us from having to actually pass in the address of the constant flow agreement as well below the host, right? So this just lets us pass in the address of the host contract, and then we also get the address of the deployed instance of the constant flow agreement contract on that network using this little syntax here, okay? So the CFA v1 library is set up. This is going to allow us to work with money streams really easily, and you can take the exact same logic and put it in your contract too for working with all of your money streams as well. Okay, so that's basic setup. You can see the similar thing done in the money router contract example. It's almost exactly the same up until this point, and now things are going to get a little bit different because it is a super app. So recall that super apps have these callbacks that are run automatically on certain operations. And we have to ask ourselves, how does that happen, right? Because if a function is going to be called, something has to call it. And the thing that calls it within the Superfluid protocol is the host. So remember, the host is like the brain of the protocol. And for the host to know that it needs to call the callbacks on this contract whenever a Superfluid specific operation takes place with regard to that contract, is we have to register it with the host. Okay, so to do this on testnet, it's very easy. We can just pass in our own config word, which just defines which callbacks you want to implement. If we want to do this on mainnet, you also need a registration key, just because super apps are really tightly tied in with the protocol, and you do need to go to our governance and request one in order to actually deploy it on mainnet. But because we're just going to be deploying on the Goerli testnet in our case, you don't need that key. So we can just use host.registerapp. But what's key to understand here is what this config word is. So what are these different parameters in this config word that we need to use to make sure that this all makes sense and that it's registered properly? Okay, so the first thing we need here is we need to define the app level. So app level is just a fancy way of defining how many super apps can be chained together in one consistent string. If the app level final is 1, it means that your super app is it's effectively the final app in that chain of money streams, and you can't chain super apps together that can keep calling each other in a cascading way, right? This is actually a protocol level thing right now, so the only option you really have is to just put 1 there. And the reason why we're able to just do this is because the current app level final is 1, right? It's a protocol level function. It's a protocol level variable. It's already been set. We can already get it from the super app definitions, which we pull from this import here. And that's basically already set, right? This is just kind of boilerplate that you need. And the other 3 things we're going to do in our case is set 3 of our callbacks that could run to not run, right? So by making them all no ops here, by setting it up like this, what we do is prevent any of the before agreement callbacks from running. So there are 6 total callbacks you can have run, right? There is the after agreement created, the before agreement created, the after agreement updated, before agreement updated, and after agreement terminated and before agreement terminated. In our case, if we scroll down, we're going to use all of the after agreement versions. So what we need to do is to ensure that those are called, but the before agreement versions are not, we need to set all these as no ops. So that's going to all go into our config word. All this information will be packaged together inside this config word, And then we will pass this as our loan variable to host.register app to let the host know that it only needs to call the after agreement callbacks. Okay? Again, might be a lot of information. You can read more about this in our docs and in our wiki in GitHub. And if you have any questions, please feel free to put them in the comments or reach out to our dev team directly. Okay? So that is the setup for a super app. What we now need to do is think through the logic that needs to run here. Okay? So I'm going to go down to our callbacks and show you what needs to exist there. And then we can build up and write the actual function logic that needs to be executed there. Okay, so we have the 3 callbacks that I mentioned earlier that all need to run. One of them is after agreement created, the other is after agreement updated, and the other is after agreement terminated. You can see that inside of all these functions, we're going to execute a specific function here, right, that is called updateOutflow. And each of these callbacks has a couple of modifiers. Okay, so let's go through the modifiers first. Now, one of the most important modifiers here is the only host modifier, right? You don't have to build a modifier. You can also just run a require statement at the beginning to ensure that the caller is the host. But we want to make sure that only the Superfluid host contract, again, the brain of the protocol, you'll hear me say that a lot, we want to make sure that that is the only contract or address at all that can call these callbacks, right? Because if we allowed anybody to come in and call the after agreement updated function, it's going to create unintended behavior and potentially a very large security risk for us. If we were to allow this inside of our own application here, it would mess with our logic and make the contract somewhat insecure. So we don't want to do that. We want to be careful about who can call these callbacks. That's where the only host comes from. Another modifier we're going to use here is the only expected. This is designed specifically for us, but what it's going to do is make sure that the only token being used within these callbacks is the we run this is same token, right? So we want to make sure that the token being used is the accepted token that we defined up here at the top. So the token being streamed in and run when executing the callbacks should be the token that we pass into accepted token. If there's a different token passed in, it should reject that. All right? And then finally, the other parameter here that we include inside of the only expected is the agreement class. So we want to make sure that the only agreement being used is the constant flow agreement. Now, the constant flow agreement, for those of you that don't know, is the agreement that facilitates the streaming of money. There are other Superfluid agreements. There are some that are in the works that are a bit futuristic right now, like the decaying flow agreement. We won't talk about what that is today, but the other one that is live is called the instant distribution agreement. And the instant distribution agreement, if it's used with this contract, will trigger callbacks unless we specify that it should not. Okay? So the only expected modifier will take in the agreement class and make sure that the agreement being used is indeed the constant flow agreement, so that if this contract were to be somehow added to an IDA index, that wouldn't somehow trigger one of these callbacks, because we wouldn't want that to be unintended behavior. We're not planning for that. We're keeping our logic constrained to what we want to do. That's good smart contract development 101. You want to really confine the potential state changes within your application or your contract to things that you have well-defined, and always keep your individual users' security in mind. Okay? So we went through those, right? That basically constitutes this entire bottom portion, right, which walks through our modifiers. Now we need to walk through the updateOutflow function, okay? And one more thing, just to make sure that we're on the same page here. Inside the after agreement terminated callback, we need to be very careful, okay? You cannot have a revert inside of the termination callback. So what we do is we make sure that it's not going to revert by ensuring that this same token and CFAV1 are, like, we want to check here first before returning this updateOutflow function, because, well, if these were incorrect and we just had them as modifiers, this whole thing would revert, okay? So we don't want that to happen. We don't want there to be a revert inside the termination callback. That wouldn't be good. So we've added this extra check here because there does need to be some extra security considerations inside the termination callback. Again, I won't go too deeply into this one for right now because it is a pretty dense topic. Just keep in mind, you can't revert inside the termination callback, and you can read about it inside of our docs, which I will link to below, specifically around security in the termination callback. Okay? So let's get into the update outflow. All right, so the update outflow function is going to give us what we need here. Okay, it's going to give us this ability to automatically redirect incoming streams to the owner and then make sure that it always balances out such that there's no difference between the amount of money going into the contract and the amount of money coming out of the contract. Right? That's our goal. Our goal is to have a net flow rate of 0. Right? There shouldn't be any more going out or any more coming in. It should be balanced. Okay, so let's go up to the update outflow function. What does this need to look like? Okay, so the first thing we're going to do is we're just going to set this new context variable we need to return to this context variable here. Okay, one important thing to remember about super app callbacks is that you have to return a context value. You can see here inside of the callbacks themselves, all of these are returning this new bytes value called new context. So context is a technique used within the Superfluid protocol to pass serialized validatable context between an external call, right? So if there's a call made to the Superfluid host contract, we need to make sure the context that that call was made in is passed properly into the host contract, and that the host contract, when it calls the Superfluid callback here on the super app, that it returns an updated version of that context. Okay, so what we need to make sure of is that when a context is passed into a function, that it also returns one. Okay, so the update outflow function is going to receive a context, right? It's going to get a context. It also needs to give a context. It needs to return the most updated context, right? That's what the protocol needs, and that's what we'll do. Okay, so what we've done here is set this value equal to our context value. Okay, so then what we need to do is create an int96 variable. We're going to call net flow rate. And what we're going to do here is call cfav1 lib.cfa. Okay, so we're going to call a view function on the constant flow agreement contract to get the net flow of the specific app. So get net flow. And we're going to pass in the token we're getting the net flow on, accepted token, and then the address of this. Okay. So what this is going to do is give us the current net flow of the contract. This should be 0, right? The goal is for this to be 0. Now, when we call it within the callbacks, it might not be 0. So we need to be able to handle that situation properly, which is what we'll do in the rest of this function. The other thing we need to get is another value here, which we need to pull off from a get flow call, not get net flow, but a get flow call. So this is going to be the outflow rate. And I think there's one more comma there because it returns 3 values. So this is going to be cfav1 lib.cfa.getFlow. And in a get flow call, we need to pass in the sender, the receiver, and the token, right? Because we're getting the information about a specific flow between 2 addresses. Okay, so this is going to include the accepted token, the sender. So in our case, if we're going to get the outflow rate, we need the outflow rate from the contract. So the sender is going to be address of this. If I could type. And the receiver is going to be the receiver that we set there in the beginning. All right, so that's been done. Now to get the inflow, what we can do is add together the net flow rate plus the outflow rate. Okay, that's our goal. So then we can start running some logic, right? We can start running some conditionals. So if the flow rate, the inflow rate that is equal to 0, we need to delete the outgoing stream. So if inflow is equal to 0, let's cast this to make sure it lines up. int96 is 0. What we need to do is call cfav1 lib.delete flow with context. Okay, so why with context? Well, remember that we need to return a context value. Now, if we go to a different example, right? If I go to a different example inside of our repo, if I go to the money router example and I search create flow, let's find one where it's just vanilla. We're just calling create flow. We don't need the create flow with context because we don't have to return a context. If we had to return a context value or if we had to pass in a context value, we need to use create flow with context. What create flow with context will do for us is take in a context value and then return a new one. It is what we need to use when calling a specific CFA operation inside of a super app callback. So anytime you're writing one of these functions inside of a super app callback or one that's meant to be executed inside of a super app callback, you need to use the with context version. So the first parameter that it's going to take is the new context value. And then it's just the standard other stuff, right? So we pass in the address of this, receiver, and the accepted token. All right. So this flow is deleted. How about a different case, right? So maybe we have an else if case. Let's say that in an alternative option, if the inflow rate is not equal to 0, but the outflow rate is also not equal to 0. So let's do outflow rate. Of 0. What does this mean? Well, this means that there is an inflow rate. And the current outflow rate is not equal to 0. All right? This would mean that we need to call an update of the outflow. We need to make sure the outflow matches the inflow. So let's do this. I'll call CFAV1lib that update flow with context. New context is the first thing we need to pass. Then we need to pass in the receiver. Again, this is the outflow, right? The outflow is the receiver. That's who it's being sent to. You need to pass in the accepted token. Then we need to pass in a flow rate. So what's the flow rate? Well, it needs to be the inflow rate because we need to make sure that the outflow rate matches the inflow rate. That's our goal. And let me go up here actually and make sure that we actually have even named the inflow rate variable. Okay, done that. And then finally, what if both of those aren't true? Well, that means that there's no outflow rate and there is an inflow rate. So the outflow rate is equal to 0, but the inflow rate is not. That would mean that we need to create a flow from the contract to the receiver because the previous inflow rate was 0 before this call is run. So we can call CFAV1lib, create flow with context, pass in new context, and then say the parameters look exactly the same as in the case of the update, right? So this is going to be sent to the receiver in the amount of the accepted token, and the inflow rate is going to be the outflow rate. Boom. The final thing we're going to do, I guess we don't need to do anything else here. All right, so now we have the update outflow function. Wonderful. Next, we need to make sure that the changeReceiver functionality works. So if I transfer the NFT to somebody else, we need to make sure that the stream to the old owner is deleted and a stream to the new owner is created in an amount that is equal to 100% of the previous flow. Okay, so inside of the changeReceiver function, this is going to have a couple of require statements here up top. So we're going to make sure that the new receiver is not the 0 address, and we're also going to make sure that it's not a super app because remember we can't chain super apps together, right? That's important. We're also going to emit this event down here. Let me make sure that I have this event created. Yep, we got this. This is going to be emitted just to make sure we spit this off so that in case we want to do analytics, we can get that information. And this function is going to actually run inside of the NFT contract itself. There's a different hook we're going to implement there. We'll get into that in just a second, but keep in mind this is going to run each time the NFT is transferred. All right, let's get this underway. So the first thing we need to do is, one, we need to see if the new receiver is equal to the receiver. And if it is, we're going to return. So this is going to handle the case of the mint, right? So this is going to get minted when we first deploy it. We need to make sure that it just returns and doesn't do anything else in that case. But if it's not, then we need to do some other things, right? So the first thing we need to do is get the outflow rate, right? We need to get the current outflow rate from the contract. So this is going to just allow us to do, we'll do the same thing we did up here, getting the outflow rate. It's going to look very similar. So it'd be int96, outflow rate, and then I think it's 2 commas, right? 2 commas, is that right? Yep, 2 commas. Nice. So it'd be CFA v1 lib dot CFA dot get flow. And the flow there is going to be the accepted token. The sender is going to be the address of this, so how much was currently being sent from this contract to the receiver. And boom, we have our outflow rate. If the outflow rate is greater than 0, so if any flow exists at all, we need to delete the flow. So in this case, we don't have to use the fancy with context version. We can choose the standard delete flow. So CFA v1 lib dot delete flow. And let me make sure that I called this correctly in my previous examples. CFA v1 lib. Yeah, okay, we did. We always use the CFA v1 lib. That's important. CFA v1 lib dot delete flow. And this is going to just be accepted token. Actually, no. I have my parameters wrong. It's got to go in a different order. This is going to be address of this first, the receiver, and the accepted token. All right. And the other thing we need to do is create a flow to the new receiver. So we have the new receiver passed in as a parameter here. Again, this is going to be done inside of the NFT contract itself. So what we need to do is create a new flow. So CFA1 lib dot create flow. And the first parameter here is going to be the new receiver. It's going to be the individual receiving. Second parameter is going to be the accepted token. And then we also need to get the flow rate. So we need to figure out what the net flow rate into the contract is after the deletion happens, right? So if the outflow is just deleted, the net flow rate is going to give us the total amount coming into the contract. So here what we can do is call CFA v1 lib .cfa.get net flow. And the parameters here will be the accepted token and address of this, okay? And finally, we need to set the receiver equal to the new receiver to make sure that's updated for future iterations. Okay, so what we just do? Well, we just checked to see if the outflow rate was greater than 0. If so, we deleted the flow to the previous receiver, which we have here as the receiver. Then what we need to do is create a flow to the new receiver, which is passed in as our loan parameter. So we pass in the new receiver, in the accepted token, and we set their flow rate equal to the amount of money coming into the contract, okay? Boom. So that's done. We also are going to emit an event here at the end to make sure the receiver was changed. And the final thing I want to do here is just add a view function in case we need it so that we can check to see some information about the current receiver and how much money they're being streamed. So in that case, what we can do is just call this, we're going to call this current receiver. All right. It's going to be external. We're going to return a few things. We're going to return a uint of 256 of the start time. It's going to be the timestamp. We're also going to return the receiver and the flow rate. So this is going to be an int96 flow rate. All right. So if the receiver is not equal to the 0 address, what we could do is call getFlow and get some information about it. So there are some other parameters you can get when you call getFlow. You can notice that every time I'm getting this outflow rate value, I'm skipping over some parameters that I might otherwise want. One of those parameters is, for example, start time. So we want start time with the flow rate. And we're going to get this by calling cfv1lib.getFlow. So in this accepted token, from the address of this to the receiver. And then what we're going to do is set the receiver here to our current receiver. So this is just going to return our start time, our flow rate, and then the receiver value there. Okay, so just in case you want to get this information explicitly, if you want to call it from outside the contract, we can do that. All right. So this is all done. The redirect all contract is done. This is the logic we needed to implement all the tradable cash flow functionality. Now we need to tie a bow on this by going through the actual NFT contract. Okay, so this is already done for us. This is very simple. Again, it's like 34 lines of code, right? And the key thing here is it inherits from the ERC 721 contract and the redirect all contract. So in the constructor, we need to pass in both the standard things you pass in for an ERC 721 and the parameters we need for the redirect all. So we need a host, accepted token, and receiver. We have the host and the accepted token. In our case, the owner of the NFT is going to double as our receiver. And then we need to pass in the name and symbol. Okay, so immediately what we do in the constructor is we deploy here in ERC 721. We make sure that the correct parameters are passed to the redirect all contract. And then we mint the ERC 721 to the owner with a token ID of 1. So this is going to become our receiver address. All right, that's the owner, right? And the owner is also going to be our initial receiver on the redirect all logic. So that's it. The NFT contract will inherit everything from redirect all to make sure that all the cash flows coming in equal the cash flows going out. But the key thing here is that we needed this extra hook that's actually available inside the ERC 721 Open Zeppelin API. You can read about this there. It's just called before token transfer. This will run, and this is something you can implement on ERC 721 contracts to run each time the ERC 721 is transferred. So before the token is transferred, before the call is completed, we want logic to take place. We want our contract to do something. And in our case, what we're going to do is change the receiver. So we're only going to make use of this to value, right? The new receiver value. And we're going to pass the to value, right? So this is the address of the new receiver to the changeReceiver function. And luckily for us, that is all we need, right? Because inside of the changeReceiver, we have the value of new receiver here. And this is internal. So only the contract itself can call it, which we definitely do right here. Okay? So that's the entirety of the tradable cash flow contract. Now what we can do is interact with it. So we're going to deploy it, and then we're going to interact with it such that we can see that, all right, it's minting a token properly, and all of the streams coming into the contract are being sent to the owner. Okay, so let me go in here, make sure everything looks good. Maybe add a little bit of context here that this is going to be the initial owner. Okay, so let's run our deploy script. And what I'm using for this is the Hardhat deploy library. You can install it from npm if you like. And if you'd like, you can also just use a traditional deploy script to do that here in the scripts folder. But what I've done is use this library so that we can deploy the contract by minting to this owner with the name Tradable Cashflow, the symbol TCF, and then we'll pass in the host and FDIX address for the network we're going to be working with. In my case, I've manually passed in the owner. I've also manually passed in the FDIX address and the host for the Goerli network. Looks like we got a little bit of an error here. I did just deploy the contract, but made a small mistake. So we just redeployed again. All right, looks like we have our option to skip here. If you ever run into issues where you do try to deploy the same contract or run the same transaction over again, you might get a similar error. I'm just going to skip the previous transaction, which Hardhat will give me the option to do. All right, so we've just deployed the contract here. So what I can do is I'm going to make sure that this is all working properly. I will pull up my wallet and we'll see what happens. I'm going to import this token. All right, looks like we have a TCF here. I'm going to add this custom token. Looks like we have our custom token. So this was minted properly to my address, which is great. Great to see. Now we can paste the same address into our scripts. So this first script, I'm going to paste in the tradable cash flow address here to the top. And what I'm doing inside of this script is just creating a flow into the contract. What we're going to be doing here is testing to see if 100% of the flow into the contract is sent to our owner. And we can do that by running the script and then going back in to the Superfluid console to check and see what the flow rates look like. Okay, so to run this script, I can run the create flow script. I'm going to specify the network. And while this waits to run, I'll walk you through how this script is working. So this is making use of the Superfluid SDK Core. And in the SDK Core, what we're doing is creating a create flow operation using this syntax here. So we've initialized the framework up top. We have the chain ID of 5, which is the Goerli network. We have a custom provider, which is just being used with our Alchemy URL here. I just have it in a .env file here. We get the address of DIX by first using this load super token syntax, passing in the symbol of FDIX. And then inside of the create flow operation, we can just pass in the receiver, which is our contract. We can pass in the super token, which is the address of DIX. And then we pass in a flow rate. This is going to be a pretty small amount because it is the number of tokens we're going to send per second in way, but it'll still let us see that some amount is being sent into the contract. Then what we do is go ahead and send a transaction using this logic here and make sure that it's being sent from our signer. And I know that this signer has some FDIX. I can show you where to get some FDIX in just a second, but just remember that this signer has a lot of FDIX, okay? All right, so I'm spitting out the transaction receipt here, and it looks like this was successful. So what we can do is go into the Superfluid console and see how this worked, okay? So I have the Superfluid console up here. Let's make it a little bit bigger. And what I can do is just paste in the address of our contract. We have it come up here because it knows that some amount is being sent into it on Goerli. And we can see that our sender is sending money into it, right? We're sending a small amount in it per day. We can see the stream is active. We can also see that it has an outgoing stream of the same amount. So in terms of the super token balance, the balance is just 0, right? The net flow is 0, right? It has 2 active streams, but they're completely balancing each other out, right? So if we go into our owner address, we should see that some amount is coming in. So let's go back into our deploy file. I'll highlight this. And what we should see, go back, hang on. We should see when I paste this in, on Goerli, there's a new stream coming into the contract, right? We can see we have 3 active streams, so this address does have some activity. But you can see this D6 at 0.8 tokens per day is being sent. It was just created today at 2:33 p.m. where I am, and it's working. It's working exactly as we intended. Now, what happens if we update the flow? What if we want to change the flow rate? Then what happens? Well, let's just make sure that that works too. I won't go into the deletion case. We'll go into the creation case or the update case. And what I can do is run effectively the same operation, except it's an update instead of a create, right? And instead of a small amount, I've sent this slightly larger amount, but it's still going to be a small amount. Okay, so what I can do here is I'll scroll back up to the top. I'll paste over this address right here, and you can see that I've changed. This has changed a bit. I don't actually need the custom subgraph queries endpoint or the data mode, so I'm just going to delete this. from the framework initialization, but this looks exactly the same with the exception of changing the create to the update. Now what I'm going to do is just run the update flow script. So instead of create, I'm going to change this to update. All right. So the update script just finished running. So if I go back in and refresh, this usually takes a second to propagate and actually show up here in the console. But in a moment, we should see that the amount of money being sent into our receiver address should be changed. All right, so actually it was a much bigger number than we expected. So we have a different flow going into the contract at 172 tokens per day. And if you look at the receiver, we should see that this stream works properly. Okay, so there you have it. We just built the entire Tradable Cashflow contract together there. You are now equipped to build your own super apps that can take in money streams and send out money streams automatically. This is a great place for you to now go on to potentially the NFT billboard example, which will make further use of that context value we discussed earlier so that you can pass in any arbitrary value along with your streams and then make use of it inside of the callbacks. So again, I recommend going to the NFT billboard. You're now equipped to build your own super apps. And if you have any questions at all, the DevX team is here for you, right? So we can help you with building your own super apps, deciding whether or not a super app is necessary for your application. And yeah, we try to be very helpful. So join our Discord if you haven't already. Leave a comment if you haven't already. Subscribe for more videos like this. And our team is, like I said, always willing to help. So thanks again for watching, and we'll talk to you soon.